Okay, so how do I get this tunnel time? So just to give you a flavor, so again let me draw the same potential diagram. Okay, let's assume that this is a classical particle which is sitting at this origin, right? I have this x-axis, so this is my x-axis. So initially the electron is at x equal to 0 and it has to come out at this particular tunnel barrier, and we do not know what the tunnel barrier length is. Let us define this as delta L, and if the particle is coming out at some speed v, right, this is actually a kind of a tricky concept, right. So why we are able to do such a calculation is because you can make a semi-classical approximation. Those who have done quantum mechanics course would have evaluated tunnel ionization rate through a WKB approximation, right. You can make a certain classical connection to this problem, but for this, if you if you are not aware of that, just take it as a fact. But let us say I treat this whole thing as a classical particle. I have some velocity associated with this particle and it's tunneling through, and I want to find there is some length associated with this tunnel barrier. So this time associated with tunneling is just simply the ratio of the length by the speed, and this length can be written as IP by F. So how do I get this? So this is the ionization potential, right? If I want to break this threshold, this is the ionization potential, and I can easily, using simple geometry, find out that this length, right, this is, I can draw this as a rectangle. I can easily find out that this length is nothing but IP by field, because this, what is this, this slope is given by the field strength, right. This is a linear function. So this slope that I have drawn, this is corresponds to the line f times x, right. So using simple geometry, you can easily find out that this delta L is nothing but ionization potential by F, right. So now if I want to compute what is the velocity associated with the particle, I equate this half mv squared to the ionization potential, and I can compute what is the velocity associated with this. It gives you square root of 2p by m. Substitute this and the length IP by F into this TTU, and then you get an expression which is 1 by 2 square root of 2 IMP by F. Okay. A very such simple analysis will give you an estimate for tunneling time. Now if I go back to the previous slide and look at this Keldysh parameter, if the tunneling time is much smaller than the oscillation period of the laser, right, then what does it mean? That before the laser field amplitude changes, right, the electron just tunnels through. The slope keeps changing, right, as the field strength changes, and the period is associated that is T naught. Now if the tunneling process happens very fast, that means T naught is very small, then before this field, the slope of this potential changes, the electron can tunnel through the barrier. Okay, that's the basic idea. So this tunneling time and the period associated equivalently, that corresponds to the ionization potential to the Ponder motive energy, gives you an estimate for which of the processes, the tunnel process, which is a quasi-instantaneous process, that means just sees the field at that particular instant, versus a multi-photon ionization process which corresponds to the actual oscillation period, right, the oscillation of the field, which of them dominates is given by the Keldysh parameter. Now one can compute the various quantum mechanical ionization rates. So now we said that there are two particular processes. I need to, if I want to estimate how much of the, what is the probability of ionization, I want to compute the rate associated with the ionization, then there are two popular models that one can use. One is called the PPT model, named after the scientists Paramelov, Popov and Tarrant. So this is one of the formula that gives you an estimate for what is the multi-photon ionization rate, right. The rate is essentially proportional to a cross section times the intensity to the power n, and you also have what is called the ADK formula, which can be used when you want to compute the tunnel ionization rates. Okay. So these are the two popular formula one can use. For the purpose of this course, we do not really get into the details. Okay, I'll pause here. Do you have any questions? Yeah.
So basically, when the electric field is fluctuating, when it's positive, the slope will be, it will decrease the potential of the right hand side.
Right.
But when it becomes negative,
It will be on the other side.
so yeah, it will be on the left side. So the electron can then tunnel through this side.
Right.
So even if the
So you will always have, so there are basically two regimes, which means that you can, if gamma is for example much less than 1, that means TTU is extremely small. At one particular instant, everything tunnels out, right? That would be the interpret. By the time it goes back on the other side, there is nothing to really tunnel.
yes, sir, but if
Right.
T naught is weak,
If they are comparable, then both are happening simultaneously. So this ratio tells that when gamma is much less than 1, you can say that it's predominantly tunneling, right?
sir, but even if it is large, there will always be some point where the potential is still bit either on the left or the right, and it can tunnel.
Right, it can happen on both sides.
So even if T naught is very large, if T naught is very larger than TTU,
Right.
that means that if for an electron at that instant, one of those, it will always keep on changing and it can tunnel through either of the
It will tunnel through both sides. So when the laser field is on the positive side, let's say if it tunnels through this, on the negative side, your potential barrier will look like this, and then it can tunnel through this.
But maybe before it could tunnel, the barrier shifts and which is stopping it from.
Then it becomes a combination of multiphoton and right. So there is always that in between regime where you cannot really classify it as tunneling or multiphoton regime. So why people look at this is because if I want to make some estimate for how much ionization happens, it's always easy to get some analytic formula for the two extremes. So anything in between, it becomes extremely complicated to solve it. So therefore, people try to work with these two extremes so that I can make some quick estimates. Right? Otherwise, it becomes a complicated problem one has to solve. And that's the context in which these two models become important. Okay, any? Okay, so then let's carry on. So one important point maybe I should emphasize is if I look at these rates, right? So if I look at the cross section for a 1 photon ionization process, it will be greater than cross section for a 2 photon ionization process, and which will be greater than 3 and so on, right? The cross section keeps decreasing because it's a higher order process. And also you have this dependence on the intensity. If it's a first order for single photon ionization, the rate is proportional to intensity. The second order will be proportional to intensity square, intensity cube, and so on. Now the higher the order of the process, smaller is the rate. Okay, that's one important takeaway, and that means I need to pump a lot of energy or increase the intensity to be able to see some ionization happening. The second ionization rate, which is for the tunneling rate, you see that this tunneling rate depends on linearly on E, but also there is this exponential dependence. You have something like e to the minus some constant divided by E. So how does this behave? So if I have small value of E, I have a minus 1 over a small value. What does that give you? A large value. So minus some large value, which would mean the tunnel ionization rate is small, right? And if E increases, 1 over E will become smaller, right? And then you have some finite probability for tunneling. So in either cases, you need a large intensity to be able to see some ionization happening, and you see that they are also nonlinear with respect to intensity. As in the hydrogen atom example, if I need 9 photons, then the rate will be proportional to I to the power 9. That's not linearly dependent. Same way here, since I have an exponential dependence with the field, again that's a nonlinear behavior. So nonlinearity is crucial to be able to see high harmonics. Now let's go back to this model. So now if you do such a calculation like what I showed yesterday, where we saw a simple oscillation of the electron cloud with a stronger field. So something like the field strength here is 0.05, right, atomic units. Now you see that this is the initial, so again let me repeat, this is the time axis, this is psi square. And if I want to know how does the electron density look like at each instant of time, I take a certain cross section and then plot it, So initially you see that it's essentially a very localized behavior. The green color corresponds to the maximum probability, the blue corresponds to 0. To be able to see these oscillations, I have basically masked something in between. So therefore you see a blue color. But let's say I take this particular cross section here and plot it, psi square would look like something like that, okay, very well localized about the origin. Now as the laser field comes in, you see that there is something, parts of the wave packet try to fly out, and you see some kind of, let's say, trajectories. That means if I pick this particular path, so there is something getting ionized at this peak of the field, right? This corresponds to a certain peak of the field. There is something being emitted, and the maximum of that particular wave packet that's being emitted follows a certain trajectory, right? Something like that. Now there will be also a part of the wave packet, for example, this yellow part that would get emitted, that means starts flying away and then comes back and recollides with the parent atom. That means it meets this x is equal to 0 again. So you see that you have parts of this wave packet flying away at each peak of this electric field. Why does it happen at each peak of the electric field? We discussed that the ionization rate is proportional to the intensity to the power of something, or it has a highly nonlinear dependence on the intensity, and this is a higher order process, so the probability is low. So the highest probability of ionization is at the peak of the field, not everywhere. Of course, everywhere you have some probability, but you see that at each peak you see some wave packet trying to fly away from the origin. And when the field reverses, the electron wave packet is attracted back, and then you see that it recollides with the parent atom. And this is where recombination happens and you get high harmonics. Okay. So simply in terms of the time dependent Schrodinger equation, you solve this, you compute the expectation value of the dipole operator, which is related to the polarization, and take its Fourier transform, and you see that you get a lot of harmonics, and all these harmonics, right, have very similar order of magnitude, right. So they are varying about a factor of 10 to 100 here, but then you see harmonics, whereas in the last lecture where I showed these plots, you see that they will keep falling off by a factor 100 or 1000. So this is basically the origin of high harmonic generation. You drive it for strong fields and you see this nice picture, which is now the famous 3-step model that's given by Paul Corkum. So actually historically the classical picture was given earlier and the time dependent Schrodinger equation was solved later, 1 year later. But the success of the model is that of this classical model is some of the important features of this high harmonic generation spectra can be described with a very simple classical model. So the picture is you have some tunnel ionization at the peak of this electric field. Now when the field reverses its direction, whatever has been ionized gets pulled back to the parent atom. When it gets pulled back, a lot of things happen. It can recombine, it can also rescatter, or it can also try to ionize one more electron along with it. But the particular process of interest is it recombines, right, and then it emits some radiation, and this radiation is what is called a high harmonic generation. Now what are the key characteristics, right? Along with the fact that you have a number of harmonics generated with similar intensities, you also see that there is a certain typical cutoff, right? And this typical cutoff is given by ionization potential plus some 3.2 UP, where UP is a Ponder motive energy. Now this cutoff can be explained using this 3-step model. Okay, maybe I'll pause here. Yes. Yes.
The x-axis is the positional time for the.
Yes, actually this is time for all of them, but this is the harmonic order.
The green one, that's also time.
Right, this is time and that's psi square. This is x.
There is a mod psi square at a particular position.
Sorry, this is x and that's time. Yes. Right. So that's why if I want it at a particular time, I take the cross section here and then I can plot. Okay, so now we can now discuss the classical model which can give you this high harmonic cutoff. So, the classical model is simple. Let us take a one dimensional model of atom, keep it simple. Let us say it can move along x axis, the electron can move along x axis, and the field is also polarized around about this x axis, and it oscillates at this driving frequency omega naught. So, E naught cos omega naught t. Now, x is equal to 0 would correspond to the atom intact, and let us assume that at some point t prime it gets ionized. So, it starts moving. So, let us draw this x axis. This is x is equal to 0 is where the atom is initially, and at a certain time instant t it ionizes, and then it becomes a free electron, and the free electron can move under the influence of the electric field. Now, we will also assume that when it gets ionized V is 0. Okay. Why is this? So, I will go back to that particular fact that I have stated, that when I have multiphoton ionization or tunnel ionization, in general a photoionization process, the maximum probability of ionization is for the photoelectron with almost 0 photoelectron energy, and therefore, we can make an assumption that the velocity of this electron that gets emitted is 0. So, if I want to solve Newton's equation now, I need, sorry, that is an x. So, I need the initial condition for the position, which is 0, and also initial condition for velocity, which is also 0, and then I can solve this second order differential equation, and I can compute what is the velocity of this particle at a later time t, and also what is the position at a later time t. So, you can easily solve this. So, you have m dV by dt is equal to the forces, the charge times the electric field, the initial condition is given, you solve this and you get a simple equation that V at a later time t is given by E naught by m omega naught sin omega naught t minus sin omega naught t prime, right. So, that is just a simple integration will give you this. Now, I need to integrate it once more to get the position. So, for this you use the initial condition x of t prime is 0, you integrate and you get the equation that is boxed here, right. So, note t prime is a constant, right, at each point, and t is a variable. T prime is at that particular instant of time where it gets ionized. But for the real problem, I can have ionization at multiple times, right. As the field varies, there is a certain probability associated with ionization at a particular t prime, and with that particular probability an electron gets ionized, and I can have multiple trajectories that I would need to take into account to describe the complete process. Okay. So, that is the solution for x of t. Now, this you can collect all these coefficients and put them together as x naught, and this is some maximum amplitude. It is called the excursion amplitude associated with the motion of the electron. Now, what is the recollision implied? So, what is recollision? So, there is a certain later time t where the position of this particle becomes 0 again. It has started at 0 at t prime, it is undergoing certain trajectory, and at a later time ti it becomes 0. So, what does this mean? I have this general expression and I need to make x of some ti is equal to 0, which would mean I need to find the roots of this particular equation, right. So, I have equated to 0, and this is not a problem that you can easily solve analytically. So, you can set this up as a certain transcendental equation and you can solve this through plotting. Okay. There are a few, this is a transcendental equation, I just put it again on this slide. So, you have cos omega naught ti minus cos omega naught t prime is, this is a constant, again I need to remind you, and this is minus omega naught sin omega naught t prime, this is again a constant, right, and this is a constant, right, the initial condition. Now, let us say the electron gets emitted at some time t prime is equal to 0. Okay, what is time t prime is equal to 0? It would correspond to one of the maxima, right. I have my electric field is E naught cos omega t. So, it would correspond to the maxima. So, if the electron gets ionized there, I can plug this in because I have sin omega t prime at t prime is equal to 0 gives you 0. So, the right hand side goes to 0 and you get an equation which is cos omega naught ti is 1, and the solution to this is omega naught ti is 2 pi. Okay. What does it mean? The recombination time is after 2 pi, which means it undergoes a trajectory for one full cycle of the laser pulse and then it recombines after the time period t naught. It gets emitted at 0 at one peak of the field and it recombines at the next peak with the same sign. Now, if omega t prime is pi by 2, you can again solve the same problem, and you find that if you solve this problem, this equation is satisfied only if again omega ti is pi by 2. That means the electron never leaves the system. So, it gets emitted at pi by 2, but then the recombination is also pi by 2. Now, these are two special cases when you can just solve it analytically, but for the general case you would need to plot the left hand side function, the right hand side function, and then see what is the intersection point, and that gives you the answer. So, let us look at this again, t equal to 0, right. You see that it starts here and then it recombines after 2 pi, it is plotted in terms of pi, the x axis. Now, if I have pi by 2, there is only one intersection point, it just starts and recombines at the same time. Now, you can classify these trajectories into two parts. One is when omega naught t prime, that is the ionization time such that it is between 0 to pi by 2, and the ones between pi by 2 and pi. And you see that if the initial time, the ionization time is between 0 and pi by 2, that is these two cases, two examples. This is the time it gets ionized, and then I have one point where it can intersect. So, that means there is a particular recombination time. The same thing here. Whereas, if omega t prime is between pi by 2 and pi, there is no second intersection point, which means that the electron keeps drifting away and it will never come back to the parent atom. So, there are only certain emission times where I can have recombination. Okay. So, let us go back, for example, to that quantum mechanical simulation. You also see certain trajectories. When you say certain trajectories, you are looking at some parts of wave packet that are flying away. So, let us say I take this particular one, it gets ionized, but then it keeps going away, it keeps drifting away, it will never come back. Whereas, there are only certain trajectories where they can actually come back and then give you high harmonics. So, if I want recollision, classical recollision, it would mean that I need omega naught t prime in between this. Now, it is possible to solve this transcendental equation, make a plot and then try to fit that to a function, and this fitting function is again taken from this book, the reference book. You can write down a certain fit function which looks like this. Okay. This is for your information. Now, we want to find out what is the energy that is emitted after recombination, right. How do I compute the energy? So, it is the ionization potential, because once it recombines, it will release back the energy associated with the ionization potential, along with this additional energy that it has picked up during this motion in the field. This free electron has moved in the field, and during that it can pick up some energy, and that is the kinetic energy which will also get added to this ionization potential, and the energy of the photon is Ip plus half mv square. Okay. And we are also assuming, again to remind you, that V of t prime is 0. So, therefore, there is no initial kinetic energy to start off. So, otherwise I would need to subtract from this half mv square of t prime. Now, let us evaluate this. I am just plugging in that V of t that we computed in the previous slide, substitute this, and I find that the energy is Ip plus some quantity times sine omega naught t minus sine omega naught t prime square, and this particular quantity with a factor 2 is called the Ponder motive energy. Okay. To give you a little bit more physical insight into what Ponder motive energy is, if I take a free electron and then look at what is the kinetic energy, just the same kind of classical analysis, I find what is V and then find what is its kinetic energy. I find a certain value for this energy, which is E square by 2 m omega naught square sine square omega naught t. And if I do what is the average energy that this electron have during one cycle, I do a certain average, a cycle average. This, when I have a sine square function and I average it, I will get a half. So, this particular quantity has a physical interpretation, and that is what is the average energy that an electron have in a particular cycle, okay? And that is what is called the Ponder motive energy, and that is the constant that comes into this. And so, therefore, you can write this thing as Ip plus some 2 up times this time dependent factor.
So, does the velocity of the electron be 0 even after
after recombination, yes, it becomes a bound state, right? So therefore, you need to define. So yeah, it's a very good question, right? Because I am mixing up classical picture with quantum picture. So therefore, once it recombines, I do not want to define the velocity. Okay, it's a very good question. So that's why we are also starting this classical trajectory, assuming that at certain time t prime it has got ionized, right? We are not talking about the velocity earlier, but then because the maximum probability is for the electron that gets ionized with 0 energy, we are just taking that V of t prime is approximately 0. Okay, so now I have an expression for the energy of the photon that would be emitted. I also know what is V, we have substituted it here, and we also said that I can have a fitting function that will tell for a given t prime what is the recombination time. We can put them all together, that fitting function for a given t prime, what is the recombination time, plug it into this expression. So that looks a little bit complicated with all those trigonometric functions, but if you plot this, what is the kinetic energy with respect to this factor up as a function of the ionization time, you see that it follows this pattern, and you see that there is a certain maximum associated with the kinetic energy that can be released, right? That is 3 point, if you look at the numerical value, it turns out that it is 3.17, and then the photon energy would be ionization potential plus 3.17 up. So this is where this particular factor of 3.17, or you round it off to 3.2, comes in, right? So that's the maximum kinetic energy that the electron can pick up during this trajectory, starting from some initial ionization time to recombination time. So it's something that is why 3.17, it's just coming because of the trigonometric functions that you put in, the fact that your wave oscillates as a sinusoidal wave, and that's the trigonometry, and that's kind of a magical number that comes out of the fact that your driving laser has a sinusoidal or a cosine form.
Intuitively, the electron should spend maximum amount of time outside the bound state so as to gain more energy.
Not necessarily. I think I had a comment on that. Yeah, I've somehow skipped it. So if the maximum time that the electrons can spend, where is it? It is when it gets emitted at t equal to 0, and then it gets recombined at t is equal to 2 pi, right? But then it turns out that the kinetic energy that it picks up is actually 0 in that case.
Yeah, but t equals, let's say t equals 0 to t equals pi.
Yes, right. It has to spend maximum time, but also not too much, because you have this. See, ideally, a free electron in sinusoidal oscillating wave does not pick any energy. On an average, it does not pick any. You take a free electron, you shine light on it at the end of the pulse, it has no new energy. Right? Only when it gets emitted during somewhere in between the cycle, then it can pick up some energy. Okay, that's what you see here. Okay, so that's for the classical model. So what you see is that there is this cutoff that can be nicely explained using the classical model, right? You see that there is this cutoff, and you also see that the pulse would be chirped. So what is chirp? That if I look at what is the frequency content as a function of time, it's different, and I can define a chirp associated with the laser pulse. Now you see the same thing. So as a function of this time, the energy associated with the photon is different. Let's say at this particular time, the energy associated with the photon is ionization potential plus, let's say at this point, is 1 up. At this particular time, it is ionization potential plus 3 up. At this point, it is ionization potential plus some 0.7 up. So depending on the time of ionization, I will have a different frequency that is being emitted. So therefore, the pulse is inherently chirped. Okay, to quickly summarize what I have discussed in this part of the lecture, we have looked at the fact that strong fields, I have shown this during a numerical demonstration, strong fields lead to high harmonic generation. The characteristic is that you have a plateau structure which means you have many harmonics being generated with similar intensities, unlike the perturbative harmonic generation. And in order to have nonlinearity built into it, you need ionization by low frequency fields. That means you will have a multiphoton ionization or tunnel ionization. So therefore, the rate of ionization depends nonlinearly on the field strength. That's where the nonlinearity comes in. And some of the important features like cutoff and chirp of the pulse can be explained using this classical model, where you have this electron freed at a certain time t prime and then it recombines at a later time. And by looking at what is the energy that this electron picks up during this classical trajectory, you can describe a few features. Whereas quantum mechanically, it's about a small wave packet that's getting ionized and then it can come back, and there are probabilities associated with each process.
When you said it is the attosecond pulse you're saying is
Right. So the radiation which is coming from the high harmonics will be chirped.
So for it to be chirped, we said that it is being ionized at different points in time, therefore
Yes.
resulting in different rate.
Yes.
So the recombination time has to be smaller than the attosecond time.
No, the recombination time is smaller than one cycle of the driving laser pulse. Right? It's happening within a single cycle or probably half a cycle.
Yeah.
So therefore, the recombination time at most will be from 0 to pi.
So if you make given attosecond pulse, if I'm seeing multiple frequencies,
Right.
how is that possible?
Okay, I'll discuss that. So for this part of the lecture, it's more about the high harmonics. How you get attoseconds, I'll just discuss next. So you have any questions on this part? So an equivalent quantum mechanical model can also be written, and this is called the Levenshtein's model. So the classical model is given by Paul Corkum, 1993, and a quantum model, quantum mechanical description can also be given. Okay, all fine.